What is going on, guys? Welcome to this Python tutorial series for machine learning. In today's video, we're starting out with the explanation and implementation of the first machine learning algorithm from the supervised learning category. And this is linear regression. So linear regression is the algorithm that we're going to talk about today. We're going to talk about how it works, what it is, what it does, and we're also going to implement it in Python. So let us get into the explanation. So here we are again in our favorite visualization program, which is Paint. And here I'm going to explain to you what linear regression basically is, how it works, but I'm not going to get too deep into the mathematics here. First of all, because I have a blog post on that, and I hopefully will put a link in the description if you want to check it out. But second of all, this tutorial series will be more on the application side of things. So we're not going to get deep into the mathematics of the various error functions or loss functions or algorithms in general. I'm just going to explain to you what the algorithm does, and then we're going to implement it with scikit-learn or TensorFlow. So we're not getting into the deep mathematics of linear regression today. But if you're interested in that, check out the blog post. So let's take a look at how linear regression basically works. And for this, I'm going to use a two-dimensional coordinate system. And on the x-axis, I'm going to plot the time studied, the time a student studied for their exam. And then we have the score on the exam. So this is a correlation that makes kind of sense. And what we have here is a score of 100 and 0. And in between, we have 50 and, of course, 75. 25, and so on, all in between, from 0 to 100. And we have time studied from 0, then we have maybe, I don't know, let's say 60 hours. These are hours. And we have values in between. Now, what we have now is some data points, some green data points that are our students. So let's say we have someone who studied let's put some values in here. Let's say this is 10 hours, this is 20 hours, 30, 40, 50. And then we have a student that studied like 20 hours for the exam and had a 75 score. Then we have someone who studied 30 but only scored 50. But basically you could say, okay, the more you study, the better your score. So we could get a couple of data points like that. So we see a trend line here, or we actually don't see the line yet, but we see a trend here. The more you study, the higher your score. Of course, we can have someone who studies very little but has a very high score, someone who studies a lot and has a low score, some outliers basically. But that does not influence the model or the data that much because most of the points are here. And what we're trying to do now with linear regression is we're trying to plot a function which best fits all these points. And a function, I'm not going too deep into the mathematics here, but a function is basically f of x equals, and then you have m times x plus b. And what we're trying to do is we're trying to find the optimal values for m and for b. So basically how steep our function is. Let's pick a red color here. How steep our function is it like that? Is it like that? Is it like that? How steep is it? And also where it is. So is it here? Is it here? Is it here? Where is the function? We're trying to optimize, to tweak these two values to find the optimal function for these data points. And the optimal function is, of course, the function that has the least error, which means that if I have a function like this, I have some errors here. So I have a distance here, I have a distance here, I have distance here, I have a distance here, multiple distances. And as you can see, the distances are quite high for most points. So it's a very bad model. And we'll try to minimize that distance. For that, we have a specific function. I'm not going to get into the function because it's mathematical and I'm focusing on the use case here. But as I said, if you're interested in that, check out my blog post. It's the mean squared error, which is basically taking these errors, squaring them, and calculating the mean so that we have something to minimize. But basically what we're doing is we're just optimizing this line here so that we have the least error possible. Of course, you're not going to score 100% because what you could do is, of course, if you're not looking for linear regression, but just regression in general, or just a line or a curve that fits these points. Of course, what you could do is something like that, which goes through all these points. Of course, it's like not 100% correct how I do it right now, but you could overfit them all. So this would be overfitting them all, having 100% accuracy. But of course, when I add one more point, everything is screwed and it doesn't work any longer. So we're trying to make it as generalized as possible, but still pretty accurate. So we want to have a line right in between all of these points, so that we have the least error possible. And this is what we do with the linear regression algorithm. As I said, once again, if you're interested in the mathematics behind that, check out the blog post where I teach you how to implement this from scratch in Python. But today we're focusing on the use case of that and the implementation with scikit-learn. Now, one thing that I forgot to talk about is why do we even care about this red line? And the reason we care about this red line is because we try to find a machine learning model that predicts future values. So in this case, we have all these blue points here that assign a specific score to a specific study time. So as we said, we have the score here and the study time here. And what we have here are a bunch of different examples that assign one study time to a score. So I can say for this study time here, let's say that's, I don't know, 15, I get a score of, I don't know, just pretty low here. So let's say 46. But also for a study time of, I know, 13, I get a score of 65, for example. So we have all these examples that we already know the results for. And what we're looking for is a machine learning model, which in this case is a linear model, a linear line. And this model will tell us or approximate the solution or the prediction for a value that we want to know the score for. So we have a study time of, let's say, I don't know, let's say 40 hours. And what I want to know is what is most likely the score that I will end up with. And to do that, I just go ahead here and take a look at the red line and see, okay, it's around, I don't know, 75 or something like that. So this would be the score that I can expect for 40 hours of study time. Of course, this is not realistic in real life, but in this model, this would be the case. Now, also, one thing that you probably notice is that even though this line is the optimized line here because it's uh, the least wrong line, the problem is that most points are not on that line. Actually, we have like one point which is really directly on the line. So we always have an error. So if I study 40 hours, I'm probably not going to get exactly 75. I could get a value somewhere here maybe, but the regression, the linear regression in 2 dimension is just an approximation. Linear models usually become very powerful when we operate in higher dimensions. So when we have 20 features, for example, and then make a linear model or then train a linear model, this model will be pretty accurate. So of course, when we have a 3-dimensional coordinate system here, the linear model is not a line but a plane. So we are always dealing with hyperplanes. Linear just means basically flat, you could say. So a linear model in 2 dimensions is a line. A linear model in 3 dimensions, sorry, is a plane, and in higher dimensions is a hyperplane. So this is how or why we train linear models. So now let us get into the code and train a linear regression model in Python. And in order to do that, what we're going to do is we're going to import numpy as np, matplotlib.pyplot as plt for the visualizations, and import, no, sorry, from scikit-learn, which is scikit-learn, from scikit-learn.linear model import linear regression. So this is the model that we're going to use in today's video. Of course, what we need here first is data. We need some data, and in this case, I'm going to make up the data myself, so I'm not going to use real data from the real world. But of course, if you want and if you have data, you can use it. You can just import CSV files and so on. But in this case, I'm going to make up the data myself. So I'm going to create a NumPy array called time studied equals NP array, and also a NumPy array called scores, NP.array. And here we're going to put all the values. So I'm going to say, for example, we have a student that studied 18 hours and he got a score of 46, for example. And then we have another student that studied, I don't know, 60 hours and they got, I don't know, 98 as a score. And instead of just making up some random values, I prepared some values here myself that make some sense. So I'm going to copy them now. Of course, you can also use the same values if you want, but you can also use your own values. I'm just copying the values because I don't want to waste time on cam thinking about the values because of course, you need at least some correlation. The more you study, the better your score. So it's not just some random numbers here. So you need to put some thought into that. But these are the values that I just prepared for this video. And one more thing that we need to do now with these values is we need to reshape them because we now have these arrays and we have them in a horizontal format. And for sklearn, for scikit-learn, we need a vertical format. So we need to transpose the array, and we do this by saying reshape -1, 1. Basically reshape -1, 1, and I'm going to show you what this looks like. So print time studied, and you're going to see that it's now in a vertical shape, which is basically just a stack of the values. And we need that format for scikit-learn because we cannot pass just lists in there. We cannot just pass arrays in a horizontal format. So we need to reshape them. Now, the next thing that we need to do is to train them all. And this is actually very easy with scikit-learn. The only thing that we need to do is we need to create them all. So we're going to say model equals linear regression. That's it. And to now find this optimized line, to find this perfect line, we're just going to say model.fit, time studied, and scores. That's it. After that, the model is complete and it's done. So what we're going to do is we're going to visualize that. We're going to say plt.scatter in order to visualize the data points, time studied, scores. We're going to set the while limit to 0, from 0 to 100. And we're going to show the plot without the regression line first to see what it looks like. So these are the data points that we have without a regression line, without a model, and you can maybe imagine what a model could look like. Probably something like this here, a line here. But we don't have to guess, we can put in the line itself. So to do that, what we're going to do is we're going to say plt.plot, and we're going to use as x values just np.linspace from 0 to 70 for the study time, and give us 100 values from 0 to 70. And what we need as a y value is the prediction. So our model is now fit, our model is already trained. So what we can do is we can say model.predict np.linspace 0, 70, 100. And of course, let's choose red as a color here, and it should work. Of course, we need to reshape that, so we're going to say reshape -1, 1 dot reshape. Actually, not here, but here. Reshape -1, 1. This should work. Yeah. As you can see, we now have the optimized line. This is the linear regression line. This is our machine learning model. And of course, what we can do now, as I said, it's not that accurate because we're dealing with 2 dimensions here. But what we could do is we could just go ahead and say, okay, print model.predict, and I don't know, I studied 56 hours. Tell me what my score will be. And it says nothing because, of course, I have to pass a NumPy array of that. So then it should work. Okay, I have to reshape it again. Now it should work. Yeah, so it says 68 would be the score. let's check the graph. If I study 56 hours, yeah, should be around 68. Actually, that's not quite realistic, so maybe the data I copied is not perfect. It's not very good. Maybe this outlier draws the model or pulls the model down too much. Who knows? However, this is how you train the model, how you fit the model, how you predict values when the model is already trained, and how you visualize the regression line in Python. So last but not least, we're going to talk about testing the model, because up until now, the only thing that we did is we trained the model and then used it. But we don't know how accurate it is. We don't know how well it performs. We just have a model that is trained, or we think is trained, and we can use it and we can predict values. But what you usually want to do is you want to take aside some part of your data for testing. So for example, you could take 80% and train the model on that 80%, and then you leave aside 20% for testing. So in this case, I'm going to show you how this works. So we're going to say from scikit-learn.model selection import train test split, which is a function to split the data you have into training and testing data. So what we're going to do now is we're going to say time train, time test, score train, and score test equals train test split, time studied, scores, and a test size of, let's say, 0.2, which is 20%. So basically, we're using 20% of our data for testing the model. By the way, I removed the outliers or some of the outliers because if you have outliers in such a small data set, the accuracy is pretty shitty. So I improved the outliers a little bit so the values are more realistic right now. We don't have a person that studied like 5 hours and got 100% score. And we also don't have someone who studied a lot and got a very bad score because it doesn't make sense in such a small data set. So now we have the training and testing data split, and we're going to say model equals linear regression and model.fit, and we're only going to fit it on the training data. So time train and score train. And then we're going to say model.score time test and score test. The idea here is that basically we have data that we know the answer for, but we don't feed it into the model just in order to see if it can predict these values and how accurate it can predict these values. So we're going to print the score here, and yeah, basically that's it. I'm going to run it, and it says, oh shit, that's a very bad score. Something is not right here. Let me visualize that. plt.scatter, time studied, and score. Or actually, we could just use score train because we trained it on the training data. So time train and plt.show. Let's see how this looks. Of course, every time you do train test split, you get a different train test split because it sometimes takes one part of your array as test data, and in the next iteration, or not in the next iteration, the next time you run the script, it takes another part of the data. But actually, the training data looks quite good, so I don't know why the score is that shitty. Okay, now we have a score of 51%, which is not that bad. But why did we get minus 130, or what was it? I don't know. Probably because we only have 2 test examples. Yeah, but now we get 60. 60 is quite accurate. Let's just also plot the regression function, the regression line. So again, np.linspace from 0 to 70, 100 values dot reshape -1, 1, and model.predict. We're going to predict np.linspace 0 to 70, 100 values dot reshape -1, 1. I'm just curious to see of course, red. I'm just curious to see how a function looks like, or what a function looks like that got an accuracy of minus something. So why is this so bad? -7 as an accuracy. It's pretty fucked up, actually. Let's see. Okay, most of the time we get a normal value like 57 or 60 or something like that. I don't know why we get some negative values. Oh, this is pretty good, 84. Maybe if I get a test size of 10%, or actually I think this might make it even worse. Yeah, because we have only one example, and if we fail on that, the model is really, really bad. Yeah. I think what we get here is basically just the mean squared error, that is the difference or the distance to the function. So if you have a point, if you have one testing example, because 10% of that is probably just 1 point. If you have 1 point and that point is above the line, you probably get a negative score because you have to go down like 40 score. I think that's the reason why. Um, so actually, we should be able to improve that by increasing the testing size rather than decreasing the testing size. So choosing 30% might improve that. We should get more normal values here. Yeah, 73. So what I think is that if you get like something like -40, what actually happens is that you get negative distance, and then it converts it into percent. So you're basically -800% off what it should be. So in this case, it was -8%. Yeah, 80% is pretty accurate. So, however, be that as it may, this is how this works. This is just how you split training and testing data and how you test and evaluate your model. So that's it for today's video on linear regression. I hope you enjoyed it. I hope you learned something. If so, hit the like button to support this channel. Also, feel free to ask questions and give feedback in the comment section down below. And of course, subscribe to this channel if you want to see more free videos in the future. So thank you very much for watching. See you in the next video, and bye.